Given two vectors in R2, say this is the vector v1 and the vector v2 is y1, y2, and let's suppose that these are vectors in R2. We define the inner product of these two vectors as the number x1, y1 plus x2, y2. For example, the inner product of the vector 2, 3, inner product with negative 1, 4, is the number negative 2 plus 12, which is positive 10. Let's provide a geometric interpretation of this inner product. Let me remind you first the cosine law. If we have a triangle and this angle is theta, and if this is A and this is B and this is C, then we have that C squared is equal to A squared plus B squared minus 2 times AB times cosine of theta. Using this property, we have that if we think about the vector V equal to x1, y1, and the vector W equal to y1, y2, then we have that this vector that goes from here to here, this is the vector V minus W, which is x1 minus y1, x2 minus y2. Then the length of this vector, which is just V minus W, that product with V minus W, which by the way is x1 minus y1 squared plus x2 minus y2 squared. If we call this C, and this we call this theta, and this length A, and this length B, is equal to A, which is the dot product of B with B, plus B squared, which is the dot product of W with W, minus 2 times the square root of B dot B times the square root of W dot product with W times cosine of theta. But then doing the math, this part on the left is equal to B dot B minus 2 times B dot W plus W dot product with W, and this is equal to B dot B plus W inner product with W minus 2 times the length of B, the length of W, times cosine of theta. In general, the length of a vector is just the square root of B inner product with B, and for example, the length of B1 is the square root of B1 dot product with B1, and this is just the square root of x1 squared plus x2 squared. Therefore, this cancel out, and we end up with this formula. B dot product with W is equal to norm of B times norm of W times cosine of theta. As a consequence of this, we get that the angle between two vectors, cosine of theta, is just the dot product of B and W over norm of B times the norm of W. And then we have several observations. B dot W is equal 0 if and only if the angle theta is 90 degrees or 270 degrees, or which is equivalent if B is perpendicular to W. We can also say that if this inner product is bigger than 0, then the angle is an acute angle. Then theta is between 0 and 90, and when the dot product is bigger than 0, then the angle is an obtuse angle. Let's do an example. If we consider these two vectors, 2, 3, and -1, 4, we call this the vector v, and this the vector w. This is v and this is w. Then we can compute this angle. We can do that by first computing the length of v, which is the square root of v dot product with v, and this is the square root of 1 plus 16. This is a square root of 17. We can compute the norm of w to be equal, and this is equal to a square root of 4 plus 9, which is a square root of 13. And then the dot product of v and w is just 10. That means that the angle between these two satisfies that cosine of theta is a square root of 10 over a square root of 13 times a square root of 17, and therefore theta, using the calculator, is cosine inverse of 10 over a square root of 13 times a square root of 17, and this is equal to 47.73 degrees. The same interpretation works in general. If we define the dot product between two vectors in Rn, let's suppose that we have v equal to x1 up to xn and w equal to y1 up to yn, and we define the dot product of v and w as the product sum x1 y1 plus xn yn, then we have that the angle between these two vectors satisfies that cosine of theta is just the dot product of v with w over the norm of v, which is the square root of v dot v, times the norm of w, which is the square root of w dot w. And the reason is because if you are working in Rn, then these two vectors are going to lie in a plane, and then the same argument that we did with a plane with using the cosine law will work here, and then we will have this property.